I'll give
Yeah,
you a
sure,
very brief
yeah.
introduction and then
Ready
we'll
when you are.
go. So it's we have today just one talk this morning by Amin Coja-Oghlan. He is, let me see, he's worked extensively in random KSAT and random graphs and statistical physics. And he asked oh, I should do a little bit of housekeeping here. If you want to ask any questions, please type them into the chat window or the Q&A window. If you're an attendee and want to be upgraded to a panelist, just raise your hand, and Omid or I can upgrade you. If you have questions during the talk, again, put them in the chat window. Possibly I'll interrupt Amin, and otherwise we'll save the questions for the end of the talk. And without further ado, let's get started. Amin speaking about belief and survey propagation.
Thank you. Yeah, so in this talk, I would like to share some ideas about random KSAT, and in particular, I'm going to present some algorithms that stirred quite a bit of excitement about 20 years ago, and that are rooted in ideas from statistical physics. So for the experts in the audience, this might all be well-known stuff, but I was kind of laboring under the assumption that most of the audience are not experts on random satisfiability. So I'm going to give a bit of a survey on these ideas from statistical physics. There's quite a lot of material, and if I don't get through everything, maybe it's not the end of the world. So just let me know when I'm going too quickly or too slowly, and I will be happy to accommodate everybody. Okay, so about 20 years ago, this picture here caused quite a bit of excitement. Here you see the performance of various algorithms on randomly generated 4-set instances. So these are random satisfiability instances with clauses comprising 4 literals. And M is the number of clauses, N is the number of variables. And the key parameter in random satisfiability is the clause to variable ratio. So how many more or how many fewer clauses you have than variables. And in this picture, you see on the x-axis this clause to variable density as a parameter. And these bars here indicate up to what point various types of satisfiability algorithms succeed. Z-Chef was a well-known SAT solver at the time, I understand, and SCB stands for shortest clause with backtracking. And this was the best rigorously analyzed algorithm on random satisfiability instances at the time. And these 3 bars down here are new algorithms that were proposed in this paper by Mezar, Parisi, and Zekina, 3 physicists. And these were all experimental results. So they tried out their algorithms on randomly generated satisfiability instances. And as it turned out, these new algorithms, in particular survey propagation, this last algorithm here, outperformed the existing algorithms that had been developed in the combinatorics and computer science communities rather significantly. So at the time, this was like our worst nightmare coming true. There was this problem that we thought may be computationally difficult or challenging or intractable or something like that at the time. We didn't have good algorithms, and then a physicist comes along and proposes a better algorithm. So that was quite a shock at the time. And in this talk, I would like to discuss how these algorithms are supposed to work, belief and survey propagation, what the ideas behind these algorithms are, and what we know about them mathematically at this point. So let me first talk a bit about random KSAT in general. The distinct feature of random satisfiability is that there is a satisfiability phase transition. So if you fix any clause length, like for example 3 or 4, and you take a number of Boolean variables, some n Boolean variables, and now you add random clauses one by one, then obviously what happens is that the probability that you can satisfy all the clauses simultaneously drops as you add more and more clauses. But in random satisfiability, it turns out that this drop in probability, the probability that you can satisfy all the clauses, that this probability does not drop uniformly or linearly or anything like that, but turns out that there is a sharp threshold where suddenly the probability that all the clauses can be satisfied drops from 1 to 0. So there's a sudden drop at a particular threshold that depends on the number of literals in each clause. And you can try and run experiments to pinpoint or at least approximately see where this drop occurs. And this point is what has been called the satisfiability threshold. At first, this was pointed out experimentally, and subsequently, quite a bit of research on the mathematical side has been devoted to this question. And in a very important paper in 1999, Friedgut proved the existence of a sharp threshold for satisfiability of this point where suddenly the probability drops based on non-constructive arguments. So his result, his proof, is a pure existence result. It doesn't actually tell you what the value of this threshold is, but it shows that there exists such a sharp drop from 1 to 0 at a certain point. A bit earlier, even than that, two independent articles, one by Quartal and Reed and one by Goethe, actually solved the problem in the special case that your clauses have size 2, that there's 2 literals per clause. Of course, that's a very special case because the two-sub problem can be solved in polynomial time. And the paper, these proofs use percolation-like ideas, so kind of classical combinatorial arguments. But a big question at the time was, what is the location of the satisfiability threshold? What are the combinatorial phenomena that cause this peculiar behavior? And also, can we actually algorithmically solve random satisfiability instances? And then came what I would call the dark ages. So in the beginning, after this problem was kind of discovered in the early 90s, people didn't really know what to do. And there were a few simple ideas and techniques out there that people tried to apply, like, for example, the first moment method. The idea behind the first moment method is that we want to get an upper bound on this particular value, on the satisfiability threshold here. So we want to know approximately where its location is. And we, for the beginning, using the first moment method, are attempting to derive an upper bound. So we've got n variables, n clauses. And to get an upper bound, what we could do, a very simple idea, would be to calculate the expected number of satisfying assignments. So Z is my number of satisfying assignments, and using the linearity of expectation, I could simply write this inequality here. The expectation of Z is upper bounded by 2 to the n times 1 minus 2 to the minus k to the m. Where does this bound come from? Well, 2 to the n is the number of possible truth assignments of n variables. And in the random k-sub problem, my clauses are independent, so the probability that all of them are satisfied by a particular assignment is the probability that one single random clause will be satisfied to the power of m, the number of clauses. And the probability that one particular truth assignment happens to satisfy one randomly chosen clause is 1 minus 2 to the minus k, because out of the 2 to the k possible ways of choosing the signs of the literals, exactly one fails to be satisfied by a specific truth assignment. And clearly, if the expected number of satisfying assignments is less than 1, if that number goes to 0, then Markov's inequality will tell us that our random formula doesn't have a satisfying assignment typically. And doing the algebra, we get this upper bound here on the satisfiability threshold. The satisfiability threshold will be upper bounded by log 2 on minus log 1 minus 2 to the minus k, which is approximately 2 to the k times log 2. So this was, yeah, a folklore simple calculation that you could do. And also the other, I mean, just to give you an idea, in random 2-set, the actual threshold happens to be the clause variable ratio 1. So once you have more clauses than variables, your formula is not going to be satisfiable anymore. If you use the first moment bound, you get a fairly crude upper bound. You get something like 2.41, which is way bigger than the actual threshold. But be that as it may. So how about lower bounds on the satisfiability threshold? How about actually finding satisfying assignments? Well, people looked into the analysis of various simple algorithms for finding satisfying assignments, like the pure literal rule or unit clause or shortest clause. And over time, people discovered that there's one method that is very good at analyzing these algorithms called the method of differential equations, largely pioneered by Nick Wormold and in the context of satisfiability by Dimitris Akliopoulos. Here you see the differential equations that you can use in order to analyze the unit clause propagation algorithm for random 3-set. And what these results, what these analyses gave was that your random your random set formula is going to have a satisfying assignment if the clause variable density, so the number of clauses divided by the number of variables, is less than about 1.8 times 2 to the k on k. Remember that the first moment upper bound gave us a bound of 2 to the k times log 2. So there's somehow this factor of k here that remains as a gap. So the gap between the algorithmic lower bound and the first moment bound is about a factor of k. Right, so this was the state of the art at the turn of the millennium. And we were kind of stuck on this. We didn't really have a very good idea what to do, how to proceed. But then came our very good friends from physics to the rescue. And so maybe it might appear peculiar that a bunch of statistical physicists should suddenly look into the random satisfiability problem. I mean, why should they? And it turns out that from a combinatorial viewpoint, actually, the random satisfiability problem is quite closely related to a problem in statistical physics called the spin glass problem. Now, for all I know, this might be a bit of an obscure topic in statistical physics. And it's probably, for all I know, not center stage in statistical physics. It's a problem about the magnetic properties of alloys. Like, for example, if you take an alloy of gold and iron, then this turns out to have some very peculiar magnetic properties. And the statistical physicists attempted to understand what's happening with these alloys. And one group in particular, a group around Parisi and Rizal really attempted or put forward a hypothesis of what's actually happening in these alloys and what might unlock the spin glass problem. And this was the idea of replica symmetry breaking. And once this idea was discovered, it emerged that quite a lot of problems in combinatorics actually look very much like spin glasses. If you take a closer look, you discover some similar features in many combinatorial problems, including and particularly random satisfiability. Now, of course, in statistical physics, people were interested mostly in heuristic arguments and in ideas. I mean, physicists are wondrous people. They are actually interested in reality, which is something that for a mathematician is a very rare constellation. And so in particular, these physics arguments were heuristic. They didn't come with mathematical proofs, but nonetheless, they were inspirational and turned out to actually lead to very interesting mathematical discoveries. So here's the idea of replica symmetry breaking. The idea in the context of satisfiability was to say, well, we need to look not just at whether our formula has a satisfying assignment or not, But we also need to inspect how these satisfying assignments are structured, how they are located relative to one another, and what the structure of the entire set of satisfying assignments is. A bit like linear algebra, really, where you kind of understand the problem really only once you understand things like linear independence and bases and subspaces and the kernel and so on. And so that's what our good friends from physics advised us to look into. And the hypothesis, the physics prediction was that up to a certain close to variable density of about 2 to the k log k on k, so again, almost a factor k below the satisfiability threshold, the satisfiability problem, the random satisfiability problem, is shaped purely by local effects. So if you want to construct a satisfying assignment, pretty much the only thing you have to pay attention to is local correlations. So you may have to look at a variable and the clauses that that variable appears in, and the variables that appear in those clauses, and the clauses that contain those variables, again, up to a few levels maybe. But once you get the local structure right, once you get on top of the local structure, you're good. There's no funny long-range effects, no complicated long-distance phenomena going on. Up to this clause variable density, your set of satisfying assignments is shaped purely by local phenomena, and therefore simple algorithms like, for example, simulated annealing or maybe even Walksat should be able to solve satisfiability instances, random satisfiability instances of these densities. And then something interesting happens, namely there's a phase transition that affects the geometry of the space of solutions. So this is not the satisfiability phase transition. Before and after this particular density of 2 to the k log k on k, we are going to have satisfying assignments. But what happens is that at this point, the shape of the set of satisfying assignments has been predicted to change. And at this point, this kind of contiguous set of satisfying assignments suddenly decomposes into many well-separated clusters. And apart from these clusters, also local minima develop that are going to trap, or that are predicted to trap, local search algorithms such as simulated annealing. And so this decomposition into clusters also has a particular structure. Namely, these clusters, I mean, are kind of, they admit a nice combinatorial description. Namely, you can define these clusters kind of like subspaces in a vector space. Namely, these clusters can be described by 0, 1 star assignments. So for each variable, you have one of 3 possible values now, 0, 1, or star. 0 means that in all these satisfying assignments in this cluster here, for example, this variable will always take the value false. 1 means that in all these satisfying assignments in this cluster here on this little island, the variable is always going to take the value true. And star means that it's undecided. In some of the assignments here, the variable can take the value true, and others it can take the value false. And so these encodings, these 0, 1 star encodings, effectively describe the cluster structure. And yeah, so there's kind of a, so apart from the satisfying assignments themselves, there's kind of this structure that explains how they are located, how they are spaced to one another. Even though we have this clustered structure, it turns out that the cluster volumes are very small in this entire phase. So each cluster itself is small by comparison to the entire set of satisfying assignments. And as a result, we still have some kind of a correlation decay property. We still don't really have extreme, extensive, long-range correlations. So specifically, if you look at 2 variables that are far apart from one another in the graph that describes how variables appear in clauses, then variables that are far apart are still going to be essentially independent. meaning that if you look at two variables that are far apart, like for example, variable number 1 and variable number 2, and you look at the probability, let's say that both these variables are set to true under a random solution to your problem, under a random satisfying assignment to your formula, then what we expect in this regime is that these events are independent. So the probability that x1 and x2 are both set to true is factorized. It's the probability that the first variable is set to true times the probability that the second variable is set to true. So despite this cluster geometry, we don't really have long-range correlations that if once I tell you the value of one variable, you suddenly can learn a lot about the values of many other variables that are very far away from your first variable. That changes at another phase transition point, the so-called condensation phase transition point, where suddenly these extensive long-range correlations start to appear, prevail. This phase transition is expected to appear very briefly, just within a whisker of the satisfiability threshold itself. And what happens at this point is that the very largest cluster in your set of satisfying assignments are about the same. Yes, exactly. So by distance between variables, I mean the distance in this bipartite variable clauses incidence graph, precisely right. So what happens is that suddenly the largest clusters have a volume that is about the same as the volume of the entire set of satisfying assignments. So, and now if I tell you, I just observed variable x1 and it has the value true, then that might give you a hint that maybe I'm in this big cluster here, not in that one. So given that x1 is set to true, maybe with very high probability, I'm looking at a satisfying assignment in this cluster and not at that cluster. And therefore, suddenly, maybe you might get a clue what value x2 might take, because maybe x2 is frozen, or maybe x2 has a very biased marginal probability of taking the value true inside this cluster here. So now, because the cluster volumes get quite big, we suddenly get these funny long-range correlations. However, again, according to our good friends from physics, there's a way out. Namely, if instead of looking at random satisfying assignments, we look at these encodings of clusters, these 0-1 star encodings, then we basically disregard the cluster volumes themselves. And our physics friends predict that if you look at these encodings, then you still have this decorrelation property. Then still variables that are far apart from one another are going to be independent. So if I forget about satisfying assignments and say, I don't care about what a random satisfying assignment is, I care about what this 0-1 star encoding of a random cluster of satisfying assignments does. If I choose one of these clusters uniformly at random, then suddenly I can expect to recover this correlation decay condition, according to our friends from physics. So now that's wonderful news, but what do we make of it? How do we use that information? And so one idea that you could now pursue is you could try and use this information to count satisfying assignments. And specifically, if we assume that there's no long-range correlations between variables, then we could look at the following process. We start with n variables and no clauses whatsoever. And now we add clauses one by one. And for each clause, we inspect the number of satisfying assignments of the formula without that clause that do not survive the addition of this one clause. So in other words, we look at the probability that this clause wipes out a random satisfying assignment of the previous formula, of the previous structure that we had. And because our clauses are random, the attachment points of the new clause that comes along, that is dropped down on us, are going to be far apart typically. So if I'm assuming that there's no long-range correlations, then I can say, well, the probability that this guy here is set to true is something, and the probability that this guy is set to true is something, and the probability that that guy is set to true is something, but they are going to be independent. So if I want to calculate the probability that a random satisfying assignment of this box formula down here survives the new clause, then this probability factorizes, and therefore all I need to control is I just need to control the marginal probabilities that that a random variable really in my formula is set to true. So I just need to get a handle on these marginal probabilities. What's the probability that a specific variable takes the value true under a random satisfying assignment? And once I get a handle on that, I could then try and analyze this process, try and trace this process, and compute the number of satisfying assignments that my random formula will contain in the end. And so the idea behind, and of course, in general, computing these marginal probabilities is again an intractable problem. But we can try and bootstrap on this idea of local independence again. And this is what belief propagation does. So belief propagation is based on the assumption that you don't have long-range correlations in your system, in your formula, in your random formula. And therefore, we can play the following trick. So we want to look at this process of attaching clauses, like this one here. And therefore, we need to be able to understand the marginal probability that this variable here takes a particular value, like, for example, true, in the absence of this clause here. So after I remove the clause, I want to know the probability that this guy here is set to true under a random satisfying assignment. And so let's give this quantity, this probability that X is set to true in the formula where I delete clause A, let's give that a name. And let's call that the belief propagation message from X to A. Then under the hypothesis that there's no long-range correlations, we can write down a system of equations that these messages should satisfy. Specifically, suppose I want to express the message from X to A, the probability that X is set to true, after I delete clause A from my formula. Suppose I want to express that in terms of the messages that these variables down here, these 4 variables to the left and to the right of X, send to the other clauses in which X appears. Then what I can hypothesize, so if I put on my physicist hat, what I can hypothesize is, well, suppose I remove not just A, but also B1 and B2 from my formula. Then, because everything is random, most likely these 4 variables down here are going to be far apart from one another. And therefore, their joint marginals, the probability that they jointly take some particular combination of truth values is going to factorize, is going to turn into a product measure. And therefore, the probability that X takes some particular value in the absence of A can actually be expressed nicely by a sum product formula, product because of independence, in terms of the messages that these variables down here send to the clauses B1 and B2. Now, that's quite a bit of stuff. I mean, that's quite a mouthful, right? And it's not so easy to actually formalize this and to write down the formulas for this process that you would expect to get. It's not rocket science either, but it's not something you do in 5 minutes. Anyway, so if you pursue this idea, that there's no long-range correlations and that these child variables, these 4 variables here to the left and to the right, are far apart once I remove A, B1, and B2 from my formula, then you get a set of equations that relate the messages to one another. And these equations that you get are called the belief propagation equations. And these equations are written down here in a very compact notation. I don't expect you to grasp them completely, of course, if you haven't seen them before, but just to give you an idea what they look like. So under the assumption of absence of long-range correlations, we can reasonably write down these recurrence relations here that express the messages. So again, the message from X to A is the probability that variable X is set to true under a random satisfying assignment of the formula where I delete clause A. So I first delete clause A, then I look at the remaining formula, sample a random satisfying assignment, and look at the probability that this assignment is going to set X to 1. It's a bit complicated, but not that complicated maybe. These equations, I mean, deriving these equations is not entirely straightforward, but my point is that you can actually write down a system of equations that is self-contained and that relates these messages to one another. And if we assume that the true messages are actually a solution to the set of equations, then maybe we are in luck and maybe these equations only have a single solution, or maybe they only have a single dominant solution, or maybe only a single attractive solution. And so we could try and start somewhere, for example, at the point where we initialize all the messages with 1. And we could perform some kind of a fixed point iteration on these equations down here in order to find a solution to the system of equations. And that is exactly what the belief propagation message passing algorithm does. Now, how about survey propagation? So survey propagation always works with these generalized satisfying assignments that are these 0-1 star encodings of clusters. And the details are a bit more complicated, but the basic intuition is the same. So again, we define messages where we say, well, okay, I'm going to look at the probability that in a random cluster of solutions, some particular variable is either frozen to 0, to false, or frozen to true, or unfrozen, after I remove some particular clause, and then I set up a system of equation, a kind of self-consistent system of equations for these messages. I start at some initialization, some cleverly or maybe not so cleverly chosen initialization. I perform a fixed point iteration, and then hopefully, maybe with a bit of luck, I'm going to converge to the correct solution to these fixed point equations. So, I mean, there's a lot of ifs there, of course, and a lot of question marks. And so maybe it's not a surprise that it took quite a long time to sort the details out. But, well, I mean, it's an acquired taste, but once you get into it, it makes some sense. In particular, if you grind these equations for long enough, you can squeeze out of survey propagation a prediction as to the precise value of your satisfiability threshold. Unsurprisingly, this formula involves the survey propagation messages. And because these messages actually vary from one variable to the other, so depending on the local geometry of the formula around some particular variable, some variables have, the different variables are going to emit different messages. The right mathematical abstraction of these messages is a probability distribution. A probability distribution that tells you what's the probability that a randomly chosen variable in my formula is frozen to true, for example. And this conjecture, the survey propagation conjecture for the satisfiability threshold, comes as a variational problem that asks you to find this distribution of messages pi that minimizes a certain functional. And this functional, never mind the details, actually comes out of this process that I described earlier, where you attach one clause at a time and look at the probability that a random cluster of solutions to your previous formula survives this attachment process. So it's not entirely straightforward. It's not trivial, but there's some combinatorial meaning behind it. Namely, you trace this attachment process, and if you stare at it long enough, and if you sit down and do the calculations, you get these beautiful formulas down here that involve a lot of randomness. It's maybe surprising that for a problem that is easy to describe like KSAT, you end up with the formula like this, but you do. The good news about this is that this is self-contained. So you end up with an optimization problem on the space of probability measures. The problem is in closed form. It's self-contained. You don't need to know anything about satisfiability to think about this problem. So it's an analytic problem that you can look at and maybe eventually solve. So of course, I mean, this was quite something at the time, and people set about proving these physics conjectures and attempting to develop rigorous methods to get to grips with them. And one of the techniques that was developed and that has by now been or become one of the mainstays of probabilistic combinatorics, I would say, is the interpolation method. This is an idea that we borrowed from spin glass theory. It was transformed into satisfiability problems by Franz and Leone and Panchenko and Talagrand. And this method it looks a bit like cheating if you see it first, but it actually works. This method is a very much enhanced version of the first moment method. I don't have the time to explain it in much detail, but you can, in many contexts in combinatorics where you use the first moment method, you can actually get better bounds out of the interpolation method. And the interpolation method, like the first moment method, gives you an upper bound on the satisfiability threshold and can be used to deduce that whatever crazy expression the physicists obtained using their ideas at least gives an upper bound on the satisfiability threshold. That's wonderful news. How about a lower bound? Well, for the lower bound, there was a development that started about the same time as these physics ideas started to emerge, based on a non-constructive argument, the second moment method. And this was pioneered by Akliopolis and Moore in 2002, where they counted particular solutions to random formulas called odd or equal solutions, and culminated in a truly monumental paper by Dingsley and Son in 2014, where they managed to prove the matching lower bound. Namely, they managed to prove that this survey propagation prediction actually yields the correct satisfiability threshold. However, in contrast to the old arguments, the old lower bounds, all of these lower bounds are non-constructive. They are not based on algorithms. So how about algorithms? So how can we actually try and construct solutions to random formulas? Well, one idea that you could pursue is something called the decimation process. So imagine that we have a magical oracle that for a given set formula tells us the marginal probability that a particular variable is set to true under a random satisfying assignment. Then we could actually use this oracle to sample a satisfying assignment randomly. How do we do that? Well, we go over the variables one by one. We ask the oracle, what's the marginal probability that the first guy is set to true? And with exactly that probability, we actually set that variable to true. We pursue the obvious implications of that decision, like, for example, we eliminate the clauses where the variable appears positively, and we remove the variable from all the clauses where it appears negatively. And then we go back to our oracle and ask about the second variable now in this reduced formula. So we ask the oracle, in this reduced formula, what's the probability that the second guy is set to true? We set that variable to true with the corresponding probability and so on until we are done, until we are through and found a satisfying assignment. And it's easy to see using Bayes' rule that the result of this process is actually going to be a random solution to your formula. Now, of course, we don't have such an oracle at hand because computing these marginals is a number p hard problem. But in place of this magical oracle, we could actually try and use belief propagation guided decimation. We could actually try and use belief propagation, this funny idea of conducting this fixed point iteration on our random formula. So we would launch this fixed point iteration, run it until we get tired, and then hope that maybe on the basis of these belief propagation messages, we can actually estimate the probability that a specific variable is set to true. And substitute this oracle into the decimation process. So that's one idea. Another idea is to apply the same strategy, not to satisfying assignments themselves, but to these 0-1 star representations of clusters of satisfying assignments. So never mind counting satisfying assignments. Let's go for an entire cluster of satisfying assignments. So let's first try and see who is frozen to true or to false and who is unfrozen. And once we've done that, we could then try and apply, starting from the 0-1 star vector, we could launch a local search algorithm, for example, and try to find a satisfying assignment in that way. And that's the strategy behind the survey propagation guided decimation algorithm. So we again use this message passing, these message passing equations, this fixed point iteration in order to find the survey propagation messages. Then we compute on the basis of these messages the marginal probabilities that a specific variable is frozen to true or false or unfrozen, decimate accordingly according to this marginal probability and iterate. And ultimately, we use a local search algorithm. And that is exactly what these physics-based algorithms do. Like there's a very simple version of a vanilla version of belief propagation here. These are versions of belief and survey propagation that are slightly enhanced, that use some heuristic decisions on top of the processes that I just described. In any case, so the question now, of course, arises whether we can actually analyze these algorithms. Can we actually understand where these numbers in this little diagram here come from? And can we maybe either prove or disprove that these algorithms will succeed, that they will be any good? And so again, the physicists led the way. And in a paper by Rishi Tesengi and Samajan in 2009, an analysis appeared, a heuristic analysis of these algorithms appeared that predicted that belief propagation guided decimation will work up to a particular clause variable ratio, e times 2 to the k on k. That looks a little bit less fantastic than these experimental results up here. And of course, this analysis was heuristic, so we attempted to turn it into a theorem, and we at first I succeeded on belief propagation. And to the extent that I managed to show that belief propagation is going to fail, this belief propagation guided decimation algorithm is going to fail once your clause to variable ratio exceeds some constant times 2 to the k on k. So up to the value of the constant, which according to physicists is e, this verified the prediction. And the problem is easy to describe. The problem that belief propagation guided decimation runs into is simply that the decimation process itself adds constraints to the problem. So as you assign values one after the other to the variables, you effectively add constraints to your problem. And the constraints that you add are going to precipitate long-range correlations. So this process of setting one variable at a time has the same effect, in other words, as adding more clauses to your formula, and therefore, so that's the trap that belief propagation effectively runs into. And a little later, a student of mine, Samuel Hatterick, proved that survey propagation actually runs into the same trap, and that also this algorithm is going to stall well below the satisfiability threshold, actually almost a factor of k below the satisfiability threshold, which, as you remember, is approximately 2 to the k times log 2. So yeah, that's bad news for belief and survey propagation. And also, by the time we already had another combinatorial algorithm that actually outperforms belief propagation guided decimation and matches, at least for large K, the performance of survey propagation guided decimation. So finally, let's come back to random two-sat, which was the first problem that yeah, we managed to understand mathematically. And let's see what belief propagation does on random two-sat formulas. So we can ask, if you look at a random two-sat formula below the satisfiability threshold, so number of clauses is less than number of variables, what is the number of satisfying assignments? And that question actually was first raised in a paper by Fernandez de la Vega in 2001, as far as I know. And even though a two-sat, finding a solution to a two-sat problem is an easy problem, turns out that calculating the number of solutions is actually hard. It's number p hard, so it's yeah, it's an intractable problem in the worst case. So can we solve this problem on random formulas, maybe using belief propagation? And in fact, it turns out that elementary techniques like the first moment method or other elementary ideas based on percolation will fail. So the problem is not as easy as yeah, one might at first glance expect. Anyhow, so recently, in collaboration with Dimitris Aklioptis and my students Max Hahn, Kim Roth, June Lee, and yeah, Manuel Penchuk and a collaborator, Jin Zhu from China, we managed to, Noela Müller, and we managed to solve this problem. And what we proved was that actually belief propagation for the random two-sat problem does provide you with the correct marginals and does provide you with the correct number of satisfying assignments. The difference is a bit subtle. So this dotted line, this dotted blue line here is what the first moment method would get you. And the red line is what belief propagation gives you and what the true answer is in terms of the density of clauses to variables. The difference might look small, but it's on an it's on a logarithmic scale. So the difference is actually exponential in n. So just to wrap up, belief propagation and survey propagation are very powerful combinatorial and also algorithmic ideas. However, it actually seems in hindsight that solving satisfiability instances is maybe not their strong suit. So these algorithms have turned out to be extremely useful in other areas, like, for example, in error correcting codes and decoding or in compressed sensing and some other applications. But it seems that maybe satisfiability is not the strongest application that springs to mind. At the same time, quite a lot about their performance still remains unknown. So for example, to this day, we have no idea where these numbers come from and yeah, what combinatorial phenomena are at work, and explain why these algorithms work precisely up to these values. One thing that I don't know and that I would be curious to find out is whether this idea of looking at generalized satisfying assignments like these 0-1 star assignments actually appears in SAT solving and it maybe has any uses in practical SAT solving as well. So yeah, at this point I'll stop. Thanks for your attention and sorry for going a little bit over time.
Sam, I think you're mute, Sam.
Let me try that again. I was thanking you very much for a very nice talk and encouraging everyone to join me while I clapped, since they can't clap themselves. And thank you for unmuting me, Albert. So I guess now we enter the discussion session. There was a another question in the chat window and also a Q&A question. Why don't we take them in the order that they came in? The Q&A was Sam McGuire asked, can we estimate the number of clusters above 2 to the k log k over k?
Yes.
Yes, that was from earlier in your talk.
Yeah. That's a very good question. So that's a very good question. So the basic idea would be to actually use survey propagation to estimate the number of clusters. The number of clusters has a name in statistical physics. It's called, I mean, of all things, it's called the complexity of the satisfiability problem. So there is a heuristic formula that tells you how you get from the survey propagation fixed point that you calculate to the number of clusters. However, it is very unclear whether this formula works for all densities above this magical 2 to the k log k on k threshold. And that is because of a very subtle phenomenon called full replica symmetry breaking that may be present in this regime. The short answer is it's an excellent question. We don't know.
Okay, good. Let's see. Paul Beam has a question in the chat window, and Paul did this already, but let me just remind you: when you post a question to the chat window, please direct it to all panelists and attendees so that everyone can see it. By default, it just goes to the panelists. So Paul's question is, what are the type bounds for the KSAT threshold that come out of survey propagation optimization?
Yeah, exactly. So that's another excellent question. If only I could find the slide. Right, so I mean, this slide here gives you the formulas in all their glory. And so, yeah, and so what you would have to do is you would have to find the inf of this beautiful functional here over the space of all probability measures on the unit interval. Now, that's quite a tall order because that's quite a large space. In fact, it's an infinite dimensional space. And you would have to sift through it somehow in order to find and optimize this functional over that space in order to find the true answer. So of course that's completely infeasible. And for example, for k equals 3 or 4, that's the only answer that I can give. I can say that, well, based on the axioms for the real numbers, I can promise you that this infimum is a well-defined real number. Good luck computing it. Now that's not very satisfactory, and it turns out that for large values of k, there's something better that you can do. So for the values of k that are in the Ding-Sly-Sun, for which the Ding-Sly-Sun argument works, this theorem that verifies this satisfiability threshold conjecture for large k, for the values where that works, what you can do is actually something algorithmic. In that case, what you can do is you can perform this fixed point iteration on satisfiability formulas induced by Golden-Watson trees. And if you do that for a large enough height of the corresponding tree, then you can find a distribution that approximates this inf within any given accuracy. So there's a mechanical way of doing it, of getting numbers out of it, but it only works for large k. And unfortunately, nobody knows what large k means here. And I'm guessing large means really, really large. I mean, so large that you don't want to meet this number, particularly at night. So it's not a practical answer either. In physics, of course, what people do is they start a heuristic fixed point iteration at some distribution using an algorithm called population dynamics, and they cross their fingers that maybe they are in luck and they find the correct minimizer, and to be honest, they probably are. right? So there's no simple formula for this. There's an approximation that one can get, and the approximation, I think it was on one of these slides, maybe, hopefully, maybe not. So the approximation that you can get is that the answer is quite close to the first moment upper bound. Exactly, this is quite close to the first moment upper bound. Okay.
Okay.
I think I lost track of the chat a little bit.
So the next question was from Oliver Coleman, third from the last. He's referring back to something you mentioned at the beginning of the talk. Some intuitive explanation on those differential equations would be great.
Right, yeah, it's not difficult actually. So these differential equations, are they here? They actually just describe the following thing. So Y3 is supposed to be the density of clauses of length 3 as you run unit clause propagation. So, I mean, you obviously are very familiar with unit clause propagation. And what happens in unit clause propagation is that you start with a preset problem, but then some of the clauses get shorter. And obviously, once you produce a lot of clauses of degree 1, you get yourself into some serious trouble, because at that point you are bound to run into contradictions. So you want to track clauses of length 2 and 3, and cross your fingers that you don't, with any positive probability, ever construct clauses of length 1. And so Y3 and Y2 are the densities of clauses of length 2 and 3, respectively. And these equations basically express the flow of equations of clauses of length 3 into clauses of length 2, and of course the flow of clauses of length 2 that you just satisfy. So that's basically what this does, and T is the fraction of variables that you set, that you have set already. So it's, yeah, and you can actually solve this equation analytically. It has an explicit equation for k equals 3. And if you run experiments, you see that it's, and you can also prove this, of course, asymptotically for large n. But if you run experiments, then you see that this differential equation approximation is spot on for unit clause.
And the x, what is the x?
Sorry, the x is supposed to be a t. Sorry.
Just to clarify, this means the flow as you're doing unit propagation.
That is right. That
Okay.
is right.
Okay, thanks.
Okay. All right. Okay. Ryan Williams has a question in the window. I'll read it out. For what clause densities can belief propagation approximate counting 2sat in polynomial time? Question mark. All constant clause densities less than 1. What does the number
exactly.
of sat assignments look like?
Yeah, I mean, it's exactly what we get. So exactly. So it works for all densities below 1. It's a bit unsurprising that it works for densities below a half, because in that case, your random 2sat formula decomposes into tiny little components, tiny little isolated subformulas for densities less than a half. But for densities up to 1, or for densities above a half, it's actually not easy. Because in that case, what happens is that a giant component, a huge connected component of clauses and variables appears and quickly fills up most of the, or quickly swallows up most of the formulas and clauses. And what this result here shows is that, in fact, for all densities right up to the satisfiability threshold, belief propagation gives you the right answer. And so again, the answer doesn't come, I mean, we are not entitled, I'm afraid, to a neat little simple formula, but the answer simply comes in terms of belief propagation. So I could again write a variational problem and drop that on you and tell you, well, here's an inf over a set of, over the space of all probability measures on 0, 1. Good luck finding it. But also in this case, we actually have a guarantee that using tree approximations, using effectively a finite number of rounds of population dynamics, you will get within any given accuracy of the given of the true answer. And so again, this red line here is the limit of 1 on n expectation log number of satisfying assignments for any density between 0 and any clause variable density between 0 and 1. This is actually parameterized in terms of twice the number of clauses on n in terms of the average variable degree. That's why this plot here ends only at 2. And this left picture here shows the empirical distribution of messages that you get for various densities. So these various lines here, like for example, this blue dotted line and the red line and the black line, are the CDFs of the distribution of messages for various clause to variable densities. And if you look at this for a little bit, you see that the distribution is symmetric, which is unsurprising because in this random formula, every variable or the signs of the literals are chosen randomly. So you would expect a symmetric CDF in the n symmetric around a half. But what you also see is that there's no particularly simple pattern emerging. I mean, you see a few jumps in this function in the CDF, and these come from peculiar tree formulas, little components in your entire two-sat formula. But apart from that, we expect that what you see here is a mixture of a continuous and a discrete distribution.
Thank you.
So, yeah.
Okay. Albert Zarius has a comment, a question here, so I'll read it out. Some concepts like satisfiability threshold, of course, are particular of random formulas, but the concept of correlation decay and its use for algorithms could well apply to worst case instances with similar parameters, say density or hereditary density. Any chance worst case analysis could be done?
That's a good question. So I think that's an excellent question. It would be interesting to maybe study this also in the context of ideas such as the Lover's local lemma, maybe. I mean, there has been some work in this direction already, of course, like, for example, Moitra's work. But I think it would be very interesting to look into this. I mean, there has been extensive work, for example, in the context of the hardcore model and other spin models, where this connection between something like Gibbs uniqueness and complexity has been analyzed. But yeah, for all I know, there's quite a bit of there's quite a number of white spots on the map when it comes to satisfiability. Yeah, exactly.
Yeah. Albert adds that that's the worst case. It should be emphasized. Yeah.
Yeah, exactly. So I think it's very interesting. The other question I don't know about is to what extent the SAT solving community has actually been interested in or has been looking into algorithms for counting or sampling satisfying assignments. I mean, I know there's this great body of work on clause learning and so on about finding satisfying assignments, but I don't know if there's been any similar extent of research on, let's say, sampling or counting solutions.
So,
yeah, exactly. This sort of, I don't know anything about that. So I should really learn about this because, I mean, this work on random SAT is much more of the counting and sampling flavor in some sense than of the finding.
So Paul, so one quick comment. So for those in the program, so there's work by Coja-Oghlan and others on actually trying to find to approximate the number of solutions. We did some work earlier on finding trying to do exact counts. They're difficult with standard CDCL extensions even of CDCL type solvers that try to break, if you want to do things exactly, that break things into components, you can save some things there, but they start to fail for the same reasons that SAT solvers fail on random formulas. So they end up being quite difficult. And I don't know whether the approximate solutions, for random formula instances, how they behave with respect to model counting.
Mm-hmm. That's very interesting. Yeah. Yeah, I should look into that. I don't know enough about this, I'm afraid. It would be very,
I'm not sure that they work very well in those contexts. Kuldeep might be able to it would be certainly one to talk to about that.
Yeah.
And Thomas Kochman mentioned something related on slide 12 of a possible hidden Bayesian thought, connections to Bayesian networks.
Yeah, one challenge I have with slide 12 is that I can't actually get there quickly because somehow page up and page down doesn't work while I'm sharing the screen. So yeah, I'll get here eventually. Yeah. Yeah, exactly. I mean, of course, this is very closely related to Bayesian networks, where again, belief propagation is kind of one of the killer algorithms, I guess. It's actually yeah, so that's one thing, and also it's related to the fact that these random K-SAT formulas don't contain. So if you look at this clause variable incidence graph, they don't contain a huge number of short cycles. So locally, they essentially look like trees, which means that belief propagation, which excels on acyclic Bayesian networks, works so well on them. Yeah, exactly. So what if we add a third dimension? So that's a very good point. So of course, this is. I mean, this is sort of the original idea or the original dimension that physicists would have in mind. So normally, from a statistical physics viewpoint, what you would do is you would actually fix the geometry of your problem. You would fix M and N, and you would play with another parameter called inverse temperature that effectively scans through the various qualities of assignments. So how many clauses you or how many clauses you satisfy or fail to satisfy. And that would give you another dimension. And that is exactly what normally people would study in the spin glass community. And what you see is, of course, if you kind of look at that parameter as well, you get a two-dimensional phase diagram where you have the clause variable density on one axis and beta, the inverse temperature, the quality of the solutions on the other axis. And what you discover, of course, is that, I mean, in this phase here, nothing interesting happens if you relax the problem, if you're willing to compromise and leave a few clauses unsatisfied. But here and here, what happens is that you, as you increase the temperature, as you're willing to leave more and more clauses violated, you will see that you effectively move left in this phase diagram. So here in this picture, once you make your temperature large enough or your inverse temperature small enough, you will recover the left picture.
Okay. Sue Pratik posted just to the panelists. Let me read it out to everyone. Regarding Paul's comment, indeed, for approximate counting sampling techniques, random CNF formulas pose the same problems. Jakob Nordstrom's asked a question to everyone. My understanding is that there are AI applications for uniformly sampling random satisfying assignments to a formula, and that there is some literature on this, some rigorous, some not so much. I'll be happy to apply that.
Yeah, I should really look into this. I mean, this is would be interesting to. I mean, I'm wondering if any mileage can be got out of this idea of counting clusters or relaxing the problem in some, coming up with some combinatorial relaxation, but maybe this is being done already. I just don't know much about this, I'm afraid.
So if I could ask a rather simple question, just to make sure my understanding is okay. You mentioned the Ising models were the inspiration for a lot of this. And the connection here is just that the Ising spin models are very local. You look at spins of adjacent atoms. And likewise, in random KSAT, we're looking at local connections between clauses. Is that the connection, or is there something else I'm not seeing?
Right. I mean, so the Ising model is, I mean, so at first glance is, or I mean, so the Ising model by itself is actually quite a lot simpler than these random KSAT models. And the reason is that, let's say, in the ferromagnetic version of the Ising model, there's a simple ground state. There's a simple way of satisfying all the constraints. And that is, you just polarize all your magnetic spins in one direction. For example, the all +1 solution is the ultimate configuration in your Ising model. Everybody is happy as they can ever be. And so because there's this kind of obvious ground state, this obvious solution, the problem is conceptually easier. There's something else called the Sherrington-Kirkpatrick model, or the Edwards-Anderson model. And that is an Ising model where, instead of having ferromagnetic interactions, instead of the situation where everybody wants to be in agreement, you put an interaction term between two atoms that is random. And so this interaction term is sometimes ferromagnetic, sometimes the two atoms that are interacting, for example, on a grid or on a complete graph, want to be in agreement, and sometimes they want to disagree. And with this random interaction, you suddenly get a structure that, I mean, this is called the Edwards-Anderson model. And in this version of the Ising model, you get something that is very similar to the KSAT model, where you are in the situation that a variable is dragged in two different directions by its adjacent clauses. It appears positively in some of the clauses and negatively in some others. So some of the clauses go to that variable and say, please be true, and some others tell the variable, please take the value false. So the variable is dragged in two directions. There's no obvious ground state. I mean, if I present you with a randomly chosen KSAT problem, there's, unlike in the Ising case, no way of saying, okay, I'm just doing this and everybody is happy. And so this thing that everybody is subject to influences or pressure in two different directions, that is the common feature.
Okay, good. And I had another question too, if I can be permitted, two of them. Your decimation process looks a little bit like the PPSZ algorithm for satisfiability, except there you don't use probabilities. I was just wondering, maybe it's a question for you or the audience, is there any connection between those two? Has anyone looked at those in a common setting?
That's a question for the audience.
Okay, yeah, so the PPSZ algorithm works by setting variables one at a time, and either, if a variable is forced, setting it true or false, and otherwise setting it to a value with probability 1/2, and sort of hoping for the best. Whereas you had some algorithm that set things according to probabilities based on some marginal probability calculation. So I was just wondering if there's any known connection between these two things. I'll take that as a no, I guess. Any further questions?
So I don't know whether it's a question. Yes, I guess it's a question in terms of the models for spin glasses. You know, we're used to thinking them in sort of fixed dimensions, 2 dimensions, 3 dimensions. I mean, especially 3 dimensions being particularly interesting. My recollection, and I'm trying to get it, is that things for KSAT were closer to like infinite carry trees or something like that. I'm trying to recover that, whether that's accurate or there's some other type of structure that's sort of the natural analog of that one we should think about in that context.
There's a bit of history behind this. So, I mean, the first spin glass model out there, as far as I know, was the Edwards-Anderson model on a grid or in a three-dimensional space. But unfortunately, even physicists don't have the foggiest how to solve them or what to say about them. And in fact, in physics, there's a different slants on the glass problem, which is quite related. So this is about how silicon and oxygen actually form a glass as you cool them down, as you anneal them. And there's different schools in physics that have different opinions how this happens and what the correct physical explanation is. There's Giorgio Parisi and his replica symmetry breaking slant, and there's other ideas. And I think this is a wonderful argument to stay out of as a mathematician. And so in order to make things a bit easier, what happened is that physicists started to investigate models on a complete graph. So I don't know if you know the Curie-Weiss model, which is kind of the complete graph version of the Ising model. So that's a model that you can teach in class in about an hour. And you can solve it completely, and it's wonderful, and you learn a lot. And in a similar fashion, there's a version of this Edwards-Anderson model that lives on a complete graph, where any two atoms, any two sites interact, but they interact weakly. And this model is called the Sherrington-Kirkpatrick model. And that's on the mathematical side, on the probability theory side of spin glass theory, that's the holy grail. Everybody wants to understand the Sherrington-Kirkpatrick model. There was a breakthrough paper by Talleyrand in 2006. There was a follow-up breakthrough work by Panchenko on something called the ultrametricity conjecture. So that's basically a model that is a huge simplification of the Edwards-Anderson model. Now in physics, people then try to go back once Parisi heuristically, and later mathematically, Talleyrand and others understood the model. They went back and said, well, let's try and find a halfway point between the geometric model and the Sherrington-Kirkpatrick model on the complete graph, the Edwards-Anderson and the SK model. And what they came up with was something called the Viana-Bray model. And that is basically the Edwards-Anderson model on a sparse random graph, for example, on a random deregular graph or on an Erdős-Rényi random graph. And this model was studied in 2000, 2001 by Mizar and Parisi. They made some progress. And that is how they got into random satisfiability. Because that model is conceptually, and they have things like survey propagation and belief propagation and all that stuff already set up for that model. And that model is hugely similar to random satisfiability and random graph coloring, and you name it.
Thanks.
Very good. Any other discussion or questions? All right, well, thank you again for a very stimulating talk. It seemed like people were very interested, lots of discussion, so thank you so much. Otherwise, we're done, so thank you.
Thank you.
All right.
Enjoy the rest of your day.
Yes, everyone else too. All right, good, okay, bye-bye.